Ladies and gentlemen, on behalf of the Institute of Physics, I'd like to welcome all of you to the inaugural event of水清Li Physics Lectureship. We are very grateful to Li水清Foundation for Basic Science for their support to co-sponsor this event. The purpose of this lectureship is to introduce the most advanced physics science to the general public and to promote research in physics in Taiwan. So the Gravity Society of the Republic of China and us decide we should concentrate this year's inaugural event on the development of gravity and the general relativity. And there's no one better suited to tell us the wonders and the challenges brought about by the theory of general relativity than today's speaker, Professor Kip Thorne. And Professor Thorne's research, of course, if you ever notice, cover a lot of areas, but he especially is expert on general theory of relativity and astrophysics with emphasis on relativistic stars, black holes, and now probably interstellar, and gravitational waves. And he's the co-founder of LIGO project. If you ever notice the Google News, you will hear this LIGO. It's a very important project to detect gravitational waves. And this will be the topic of discussion in tomorrow's mini workshop to be held in Institute of Physics. Now, Professor Thorne has many honors. He is a member of many distinguished academies in the world, and he became elected to U.S. National Academy of Science in 1972. And for Science Award, he has many, but one of the most recent one is 2010 UNESCO Niels Bohr Gold Medal. This is very few people obtain this medal. And besides Science Awards, he also has many writing awards. And he was awarded by American Institute of Physical Science for the Writing Award in Physics and Astronomy in 2 years, 1969 and 1994. Quite amazing. A 24 years difference, he got twice this writing award. Of course, we know Professor Thorne has written many interesting books, and Gravity and General Relativity, and the popular book. His most recent one, of course, is Interstellar, and translated to 星际效应 by 漫游者文化事业公司. And besides Science Award and the Writing Award, he also received Film Award. And that is from National Space Society in US for Space Pioneer Award for Mass Media. I guess it is related to Interstellar. And so, it's probably time. Let us welcome Professor Thorne to give us this talk about Big Bang, black holes, and interstellar.
Thank you for that generous introduction. It's a great honor to be the inaugural lecturer here, and I'm very grateful for this opportunity. I'm going to use some film clips from the movie Interstellar to illustrate ideas of general relativity in connection with this 100th anniversary of general relativity. Is it possible to turn off these lights that are shining on the screen? And so I want to begin by introducing to you the key people with whom I worked on the movie Interstellar. Mostly you will see them talking about me, but for this purpose, I wanted to introduce them to you, to give you some sense of the close collaboration that we had between me as a scientist and the filmmakers on this film. So this is a preamble to my talk about Interstellar.
We are still pioneers. We've barely begun. Our greatest accomplishments cannot be behind us, because our destiny lies above us.
The initial impetus for the project had been to say, why not examine real possibilities? Why not actually look at the real science there?
Luckily, we had Kip, and Kip is the foremost authority on all things gravitational.
They're overly generous.
Space inside here scatters some of it back, light scattering off of the surface of a rippled ocean. Neither wormholes nor black holes have been depicted in any Hollywood movie in the way that they actually would appear. This is the first time that the depiction began with Einstein's general relativity equations.
The visual effects department under Paul Franklin and everybody at Double Negative took Kip's mathematical data and they created real visual representations of what a black hole is meant to look like.
The collaboration has produced visualization of things which nobody had ever managed to do before. We potentially may have discovered a couple of new things that were lurking there inside the mathematics, inside the physics.
I worked out the equations that would enable him to do the gravitational lensing. And so you have light that comes from a star behind a black hole. It may come in, go around the black hole several times, and then come to the camera. And so you wind up with several different images of the star.
The black hole warps the space so much, it just looks like you're looking at a strange sort of funnel in the sky with this intensely black circle at the middle of it. But the gravity of the black hole draws in all the matter from the surrounding universe. And this spins out into a giant disk around the central sphere. And as it whirls in towards the center, the gas gets hotter and hotter. And this thing, the accretion disk around it, shines brilliantly. And then we found that if you then render this whole thing, you visualize it all through this extraordinary gravitational lens, the gravity twists this glowing disk of gas into weird shapes, and you get this extraordinary sort of rainbow of fire across the top of the black hole.
And I saw this disk wrap up over the black hole and under the black hole. I'd known it intellectually, but knowing it intellectually is completely different than seeing it, than feeling it.
We had determined when we started down this road that if it didn't look like something that would be comprehensible to the audience, we would have to manipulate it in some way. But what we found was, as long as we didn't change the point of view too much of the camera position, we could get some very understandable tactile imagery from those equations. They were constantly surprising. Spoke to the maxim that truth can be stranger than fiction.
We're going to write several technical papers about this. One aimed at the astrophysics community, and then something for the computer graphics community, saying, here are some things that we've discovered about gravitational lensing by rapidly spinning black holes that we never knew before. So this collaboration isn't over until we've given some sense of the things that we've learned.
So there you met Christopher Nolan first, who is the director, and he wrote the last three drafts of the screenplay. He always does the final drafts of his screenplays because he plans them in such a way that he knows precisely how he's going to shoot each scene in the movie. It's under his control. You met his brother, Jonathan Nolan, who wrote the first three drafts of the screenplay. Chris's wife, Emma Thomas, who is viewed as the Iron Lady of Hollywood, who controls things with a very tight fist in order to make a great movie. And you met Paul Franklin, who was the supervisor of visual effects, with whose team I worked very closely. And I will comment about Paul and his team a little bit later. Let me move on to the prologue then, having done the preamble. Einstein's audacity. The original title of this prologue was Einstein's chutzpah, but you have to be Yiddish or Jewish to understand the word chutzpah. Einstein had enormous self-confidence, and this illustrates it. It's the story of his finding or constructing general relativity. So the two great physicists of all time were Isaac Newton, back in the 1600s and early 1700s, and Albert Einstein in the 1900s. Newton gave us a framework for all the laws of nature, a framework that lasted for 200 years until Einstein came along, based on space and time being absolute. Everybody would agree on what they are. There's just one unique space, one unique time. Based on ideas of forces, accelerations, the things you know in everyday experience. Einstein, in 110 years ago, so this is not yet the relativity theory that we will talk about, but he gave us a new framework based on the principle of relativity, which says that all the laws of nature must be the same in every freely moving laboratory, everywhere and every when in the universe. This principle of relativity, then, is a law that governs all the laws of physics, and that takes great courage to propose a law that governs all of the other laws, controls all the other laws. Einstein, based on this principle of relativity, made a startling discovery. Suppose that I measure the speed of light, a light beam goes past, and I measure how fast it moves, and I get approximately 300,000 kilometers per second. Suppose that you are moving past me at very high speed, at a speed of 200,000 kilometers per second. Then surely it must be that you will see this light beam move at that difference between those two speeds, just at 100,000 kilometers per second. But the principle of relativity says no, you must measure the same speed as I measure, even though we are looking at precisely the same light beam. How can that possibly be? Well, Einstein gave us the answer that you and I, moving at different speeds, we disagree about the lengths, that is, the distances the light beam travels. We disagree about how long it takes the light beam to travel. And we even disagree about what it means for two things to be simultaneous, to occur at the same moment of time. There's a very precise description of that disagreement, but the fact that we disagree is a fundamental aspect of relativity. Lengths, times, simultaneity are relative to each of us. They are personal. They are different for you than they are for me. Einstein, having discovered this, figured it out, convinced he was right, without really much experimental data, but arguing on the basis of everything he knew. He then looked at Newton's law of gravity. And Newton's law of gravity says there is a force that the sun exerts on the Earth that is proportional to 1 over the square of the distance between the Earth and the sun at some particular moment of time. At some point where the two Earth and the sun are looked at simultaneously. Einstein said to himself, well, the separation d in Newton's law, who is that measured by the sun or by the Earth? They will disagree on that distance. And instantaneous measurement is measured by whom? By the sun or the Earth? They will disagree. And so Newton's law just simply fails. It can't be right. The very concepts that go into Newton's law are concepts that are not unique, not well defined. And Einstein said, therefore, Newton's law of gravity violates my principle of relativity. Therefore, Newton must be wrong. And that took, at least as seen by people like me, enormous courage to say that the greatest physicist of all time as of then was wrong. And Einstein then said, I have to find an entirely new basis for understanding the nature of gravity. He realized this in 1907. And it took him 5 years until 1912 to find a basis that really he became very convinced of. This is not yet 1915. This is not yet general relativity. But in 1912, he had a whole new description of the gravity that holds us on the surface of the Earth. I like to call this Einstein's law of time warps, though that's not what my colleagues call it. But I think it's a beautiful way to describe it. And it says that things like to live where they age the most slowly, and gravity pulls them there. Now, wouldn't you like to live where you will age the most slowly? And in fact, on the surface of the Earth, time flows more slowly than at high altitude by 1 second in every 100 years. It's a very small difference. But according to the formula that Einstein gave us in this law of time warps, that is precisely the amount of difference in aging, difference in time flow that is needed to explain the strength of gravity that holds us on the surface of the Earth. So he made the prediction, everybody can measure the gravitational pull of the Earth. From that, he said, using this law of time warps, I can compute difference of 1 second in 100 years. That was not actually tested with high precision until 1976, when NASA flew a rocket up to a height of 10,000 kilometers carrying an atomic clock. And signals were sent back to Earth to compare the ticking rate of the atomic clock, the rate of time flow up there to down on the Earth. And Einstein's prediction was verified to be correct to a remarkable accuracy, 1/100th of 1%, 1 part in 10,000. A real, truly remarkable verification. That was 1976, and this is characteristic of Einstein's work. In many places, it took 50 years until ideas that he gave to us were tested. 50 years later, they became part of everyday technology. In this case, the everyday technology, I guess I'm sorry, I don't have it there. In this case, the everyday technology is the GPS system by which, with your smartphone, you figure out where you are on the surface of the Earth. Signals are sent from satellites high above the Earth to your cell phone. And the signals are sent down with a correction so that the signals are transmitted so it looks like when they arrive at your cell phone, they are properly separated in time according to time flow on the surface of the Earth. But actually, the rate of time flow at that high altitude is different. And so it turns out, if this correction was not made in the signals by software at the satellite, correcting for Einstein's law of time warps, your cell phone would give the wrong answer for where you are. The GPS system would fail. So Einstein's law of time warps is built into the GPS system. So Einstein's law of time warp says the Earth's mass warps time, and this time warp produces gravity. Near a black hole, such as Gargantua in the movie Interstellar, gravity is enormously stronger, and so the slowing of time is enormously greater. In fact, in Interstellar, on Miller's planet, a planet orbiting around the black hole Gargantua, 1 hour on that planet is the same as 7 years on Earth. That's a very, very large slowing of time on that planet. And so you see Cooper talking to his daughter before he goes on a trip near a black hole. He warns her that when he goes near the black hole, time for him will flow very slowly, and when he comes back, she might even be as old as he is. We see him go near Gargantua to Miller's planet. He's there near Gargantua approximately 3 hours. And so his daughter ages by an additional 20 years while he's there for about 3 hours. We see her now grown up. She's a theoretical physicist trying to solve a very deep problem that's important for the movie. He goes near the black hole once again, close to the end of the movie, and comes back and meets his daughter. His daughter is now a very old woman, and he has only aged by a few months during all of this. This is a very emotional thing in this movie. This has brought Einstein's law of time warps in a deep emotional sense to 100 million people who have seen this movie worldwide. It is now very much part of everyday culture. And it's really quite appropriate that in the centenary year of general relativity, that this very important concept has been made real for so many people around the world. In 1912, Einstein also realized, I will not explain how, that if time is warped, then space must also be warped. And the first high-precision test of that was also in 1976. Remarkable, again, the same year as the high-precision measurement of the time warping, space warping. The Viking spacecraft, two of them, in orbit around Mars, the signals, radio signals were sent from Earth to the spacecraft and then immediately resent back to Earth, transponded, we say. And as Mars carried the spacecraft almost behind the sun, the round-trip travel time behaved differently than it would have if space were flat between the Earth and Mars. There was an extra travel time that became quite large when the radio beam was traveling close to the sun, large by 100 microseconds here, 200 microseconds, and so forth. Then after it passed the sun, coming back down. From that extra time of travel, it was possible to compute the shape of space so that the beam had to travel farther. And so this is a picture of that computed shape of space. And we visualize this by imagining taking the orbital plane, the orbit of the Viking spacecraft in Mars, and that's a two-dimensional surface, and think of it as embedded in, living in a higher dimensional space that's sometimes called hyperspace. And we look at it and see that this space had to be bent in hyperspace down, so the travel time would be, the travel distance, and therefore the travel time would be longer when the radio beam goes close to the sun. This hyperspace, today physicists call this the bulk. And so I will use that name, the bulk. In the movie, it's called the fifth dimension, and I will explain why it's called the fifth dimension later. But the fifth dimension, or the bulk, plays a very important role in the movie, and a speculated but important role in modern theoretical physics. Between 1912 and 1915, Einstein struggled to discover the law, which means the equation, because equations are the language of nature. So discover the equation or the law that governs, that controls all of the warping of space and time. And it was on November 25th, 1915, that he found that equation and announced it to the world in Berlin. It's called Einstein's field equation. And it looks very simple, but there is very deep mathematics inside this equation. And it is the equation that describes just how much warping of space and time is produced by the mass and the energy that are present in the universe. This warping controls the motions of stars and spacecraft and light and everything else. And this same equation also enables you to compute that. So if you understand this equation, you can make all the predictions about everything about warping of space and time in our universe. It's a remarkable feat, but unfortunately it requires some years of study of the mathematics in order to really understand what this equation is trying to say. I will talk for the remainder of this lecture about what Einstein's equation has shown to us in the past century. Let me begin with black holes. So a very brief history of the early history of black holes. In 1916, from Einstein's equation, Karl Schwarzschild, a famous German astronomer, discovered the formula that describes a black hole but he did not understand the formula. He did not know it was predicting a black hole. But he discovered the formula that today we know describes a black hole that does not spin. In 1939, Einstein looked at the formula, he misunderstood it, and he disbelieved. He said basically black holes cannot exist because he did not understand the mathematics. In 1939, Robert Oppenheimer at the University of California and the student Hartland Snyder, who had been a truck driver, he drove trucks for a living in Utah, they solved Einstein's equation to compute the implosion of a star to make a black hole. But they didn't really understand the mathematics that they had done. They partially understood it, but not at all well. It was not until the 1950s and 60s that these equations and the predictions were finally understood due to the work of a number of people, including my own mentor, John Wheeler. In 1965, Roy Kerr, a mathematical physicist from New Zealand, discovered the formula that describes a black hole that spins. And then in the 60s and 70s was what I like to call the golden age of black hole research, when Stephen Hawking and others really gave us the full description of what black holes are and how they behave. And in the 1970s, observational evidence for black holes began to come in. This is half a century that it took for physicists to understand the prediction of Einstein's equations and begin to test it observationally. It's a very long process, unfortunately, but we now have a very clear picture. As seen by somebody who lives in the bulk, who looks in on our universe from the bulk, this is the actual precise description of the warping of space and time near the black hole. Space becomes very strongly warped near the horizon of the surface of the black hole. The surface is a circle in this picture. It's actually a sphere, but you have to add one more dimension. Remember, I'm showing our universe just a two-dimensional slice, a segment of our universe. The color coding shows the slowing of time. At a place where you go from green through yellow to red, time flows at about 10% of the rate that it does out at large distance. If the black hole spins fast, then this throat in the warp geometry becomes longer. And as the hole spins, it drags space into whirling motion like the air in a tornado. But it's space that's going around rather than air. And if you're very close to the horizon, you cannot avoid being carried by the whirling space around the black hole in the same way as a straw would be caught in the air in a whirling tornado, whirling air. So these are the exact predictions of what would be seen by a bulk being looking in from the bulk, from the fifth dimension. Now, but what does a black hole look like to us? What would it look like if we were up close? For a non-spinning black hole, you can compute that by taking the warped space, as depicted here again. You have a star at that location. You have a camera here. There are two light rays that can carry an image of the star to the camera. One goes around the black hole this direction, the other around the black hole that direction. And then there is a shadow where no light rays can come through from anywhere. And so the camera sees a black shadow, and it sees two images of the star. And if I place many stars here around the black hole, then you get this kind of an image. Here is the shadow of the black hole. There are the two images of this particular star. This is from a simulation, a calculation by Alain Riazuelo in Paris. For Interstellar, Christopher Nolan said to me, he said, you help the team of Paul Franklin to compute this gravitational lensing for Interstellar. And so I worked together with Paul. He introduced me to Oliver James and Eugenie von Tunzelmann in London. And we did a version of the same calculation as Brizuela did, but for a fast-spinning black hole. And we invented some new techniques for the calculation, because using the techniques everybody had previously used, when a star went across an IMAX screen, it would flicker. It would go bright, dark, and they were not able to solve that problem except by inventing a whole new way of doing the calculation, which I will not go into, but which we have published and is now being used both in Hollywood and by astrophysicists. Of course, Paul got the Academy Award for the visual effects in the movie, including as a major component to the kinds of things of images of black holes and wormholes that I'm showing you. So here is a movie then of Gargantua, the fast-spinning black hole. It's a film clip. If it did not have a disk of hot gas around it. So if you look, you see amazing things as the camera is moving around the black hole. As a result, the star field is moving from left to right, except inside this ring, it's moving from right to left. There's another ring down in here and where the direction of the motion changes due to these gravitational lensing effects. If you look down here, in fact, I'm going to stop it and start over again. If you look down in here close to the black hole, you see images of a star created from nothing, 2 images, and then they come apart. This is due to something called a caustic in the past light cone of the camera, to use a very, very fancy language. So one of the projects that we did with the computer program that my colleagues wrote for Interstellar is we studied these caustics and the creation and destruction of multiple images. So if you look down here, just watch, you will see down there, you just saw 2 images created, came apart. Then if you watch the very end of this film clip, you will see this image annihilate with another image, not with the one that it was originally created by, but with a different image. So images are being continually created in pairs, and they annihilate in pairs. And it's really very beautiful to watch and interesting to study mathematically. And so we wrote a paper that describes the full details of this. When you look closely, you see up to 14 images in this team's simulations, up to 14 images of a single star here. And you can watch them in pairs created and destroyed. But that's not what what the black hole looks like in the movie. This is the black hole in the movie. And what is the difference? The difference is that this black hole, Gargantua, has a disk of hot gas around it, like Saturn's rings, but very hot, that is very bright. And that bright disk outshines the stars. So it's like trying to look at stars in the daytime with the sun shining. You just can't do it because of the bright light coming, in this case, from the disk. Why does the disk have this strange shape? And that's what was commented on in that first film clip I showed you. It's very simple. Here is what the disk actually is, much like Saturn's rings. Here is the IMAX camera. And in our calculations, a light ray emitted from the top of the back of the disk, opposite the camera, it is bent by the warped space around the black hole, warped space and time, and comes down to the camera like that. So the camera sees the top back of the disk as though it were here. And a light ray from the bottom back of the disk comes around the black hole, comes up to the camera, and so the bottom back of the disk looks like it's there. So this is the top face of the back of the disk. That's the bottom face of the back of the disk. And here, the light from the front of the disk just comes directly to the camera and produces this segment. There's one other thing, however, occurs here. If you were looking with your eyes, you would not see this glare. The disk would have a rather sharp edge. But Christopher Nolan insisted, we're showing a movie, and everything that you simulate on a computer has to be done as though it were seen not by the human eye, but by an IMAX camera. And so first the image was computed, and then it was sent through a computer program, and in technical terms of optics, it was fed through the point spread function of the IMAX camera's lenses. And what that did was that light scatters in the lenses of the IMAX camera, and that produces this fuzziness around the black hole. And so they measured the point spread function. For people who know the optics, they measured the point spread function of the IMAX camera that was used. And then they processed the image according to that to get precisely what this would look like to an IMAX camera. From some things that I will talk about in a few minutes, we know, in fact, that this black hole is 100 million times heavier than the sun, and its circumference is the same as the Earth's orbit. So it's a giant black hole. A black hole of just this size exists in the center of the galaxy Andromeda, which is the nearest big galaxy to our own, just this same size. Now I will return to that. Where do accretion disks come from? They're created when a black hole tears a star apart. So I will show you a film clip from a computer simulation not by Hollywood people, but by two young astrophysicists, actually postdoctoral scientists, James Guillocan and Subi Jazari. If you look up here, if you look very carefully, there's a little tiny blue dot that is the black hole. There is a star that is going to come in, go around that tiny blue dot, and be torn apart. And you will see what happens when it gets torn apart. We're watching from some great distance. So there, it was torn apart, and now the gas is thrown out in a large jet. Some of the gas is captured by the black hole to form a disk, but much of it just escapes into interstellar space. And you wind up with a very hot disk. That disk will normally have a temperature of 10 million or 100 million degrees, very, very hot. That's too hot for the actors in Interstellar to survive. And so for Interstellar, we assumed that the disk in Interstellar is very old and very cold, about the temperature of the sun, so that the actors could get reasonably close to it and survive. Astronomers do not see such old disks, so they don't see disks that look quite like the one in Interstellar, but the one in Interstellar is what you would see if the disk had a temperature of 4,500 degrees Kelvin. There is a black hole at the center of our Milky Way galaxy that weighs about 1/25 as much, 4% as much as the Gargantua. So it's small in that sense. It's still 4 million times heavier than the sun. These are orbits of stars around that black hole. This is now observational data taken by the research group of Andrea Ghez at UCLA, using mostly the Keck telescope. And she's made a film where you see the stars moving in their orbits, and you look down here, you see a star come in, whip around the black hole. By looking at how these stars move, you can see where the black hole is located and watch the stars be deflected by the black hole. And it's from these orbits that she has been able to weigh this black hole and find that it is 4 million times the mass of the sun. There are actually possibilities to see the disk and the shadow of this black hole in the next few years, the one at the center of our Milky Way galaxy, using what is called the Event Horizon Telescope, which combines data from many radio telescopes worldwide. It's a collaboration of hundreds of radio astronomers from 34 universities and institutes, including the Institute of Astronomy and Astrophysics here in Taiwan, in Taipei. And success is likely this decade. You can read about it on the web at that location. It's remarkable to me that the technology has become good enough that at that great distance of the center of our galaxy, we will likely, by the end of this decade, begin, or radio astronomers begin to image and produce images like the one of the black hole in Interstellar, somewhat different because this is a much hotter disk. It's puffed up. It's not thin like the one in Interstellar, but somewhat similar to the one in Interstellar. And there also is a gigantic black hole in the nearest large, huge galaxy to our own large elliptic galaxy, M87, that's 2,000 times bigger and 2,000 times farther away than the Milky Way's black hole. It's a 7 billion solar mass black hole, and that will also be imaged. Key to that imaging, because this is in the northern hemisphere, is a telescope being built, put together in Greenland that, again, the Institute of Astronomy and Astrophysics here is involved in, which will bring in one component of the imaging that is done jointly by all these telescopes around the world. So this will take a little bit longer until this is done, but by early in the 2020s, I expect we will have images of 2 black holes, their disks and their shadows. Now, black holes are quite weird, as illustrated by Miller's planet. Miller's planet orbits around the black hole. As I said, 1 hour on Miller's planet is 7 years on Earth. And the problem, if the black hole does not spin, is that Miller's planet can be no closer to the horizon, to the whole surface, than this location. Why? If it's any closer, the orbit is unstable. You perturb it very slightly, and the black hole will fall in, the star will fall into a black hole. It's like standing a pencil on its end. If you stand it perfectly, it will survive, but as any small perturbation, it will fall over. So the innermost stable orbit, 1 hour on the planet is 1.5 hours on Earth. And that's not what we need for Interstellar. So for Interstellar, we need a fast-spinning black hole. For a very fast-spinning black hole, the whirl of space around the black hole makes the orbit stable. In some sense, it's centrifugal forces somehow tied into the whirling motion of space. And so 1 hour in 7 years is possible. But I have to tell you, when Christopher Nolan told me in one of our first meetings he wanted 1 hour on Miller's planet to be 7 years on Earth, I told him I don't think that's possible. He said to me, I've seen you be wrong before. Go do a real calculation. I went home, I did a real calculation. I discovered that he was right, that it is possible if the black hole spins fast enough. When the movie first came out, there were a number of physicists, astronomers, who criticized the movie because you cannot have so much slowing down of time near a black hole on a planet's orbit. Again, they didn't know about rotating black holes. They had not done the calculation. And so there were some famous cases, well-known cases in that era where people backed off and said, okay, I was wrong. But it requires a very, very, very fast spin. So fast that it's not realistic in the real universe. It would be spun down just by capturing radiation. It would spin down. But our attitude in Interstellar was if something is allowed by the laws of physics and it is important for the movie, we will accept it. And even if it may not be very realistic, but at least it's allowed by the laws of physics. On this planet, there are huge water waves, 1 kilometer high. We don't have the audio. Have we lost the audio? Okay, well, you can watch this water wave without the audio. This water wave comes in, it descends on this spacecraft, and they struggle to escape from the planet before the water wave comes crashing down on them. This is the second water wave. they see one water wave every hour on this planet, 1 kilometer high. And so the question is, what causes these water waves? And just from the observation of them in this 1 hour period, I can deduce the following. The water waves must be tied to the deformation of the planet, just as the moon deforms the Earth's oceans to produce the tides. Similarly, it deforms Miller's planet, and it stretches the oceans on Miller's planet, similarly toward and away from the black hole, and squeezes them from the side. And it turns out that if this planet has not yet have one face always pointed toward the black hole, but it is swinging back and forth because it has only gotten into this orbit fairly recently. And if the black hole weighs 100 million times what the sun weighs, then that rocking period is 1 hour, and the oceans will slosh back and forth once per hour, and you get these gigantic waves. From the large size of the waves and the 1 hour period, we can deduce how much the black hole weighs, and then from that we can deduce the circumference of the black hole's orbit. So Interstellar is really very nice for physics, that you can look at what you see in the movie and you can figure this out, and you can figure out the black hole is spinning fast. So just from things you see about Miller's planet, you know how fast the black hole spins, you know how much it weighs, you know how big the black hole is. Inside the black hole, there are singularities governed by laws of quantum gravity. And let me talk about that. I'll introduce it in this way. Right at the horizon of the black hole, if you hover there, not falling in, you feel an infinitely strong gravitational force, which is why nothing can get out of the black hole. But if gravity is infinitely strong, then time stops at the horizon. It stops flowing at the horizon, according to Einstein's law of time warps. What happens inside the black hole? What can be slower than stopped time? Well, it's a little weird. What happens is time flows downward away from the horizon in what you would think is a space direction, but that really is a time direction. In technical terms, that's inside the future light cone of anybody who's inside the horizon, going downward. And so that's another reason that nothing can get back out. Everything is dragged forward with the flow of time and cannot escape. So now I'm going to show you Cooper falling into Gargantua. Late in the movie, Cooper falls in. I really would like to have sound again, but somehow we seem to have lost it. Let's just see. Yeah, it's gone. So he's falling into the black hole, and you hear him say, "I'm dipping down beneath the event horizon." And you look behind him as he says that, and so he's now inside the black hole, or just going inside the black hole at the moment. And still you can see the disk above him. So he has no trouble seeing out of the black hole, but we on the outside cannot see into the black hole. Why? Because light falls into the black hole to his eyes, but light cannot get out of the black hole to our eyes. Another wonderful thing, and again this comes from the computer simulations, is that when he's down inside the black hole, here is the accretion disk. And the external universe now is inside the disk, and the black hole is outside the disk. Because basically as he went in, the disk, the black hole appeared to get bigger and bigger and bigger and bigger, and the disk shrinks down. And so the external universe that before was outside the disk is now inside the disk. And all of this is shown quite nicely in the movie. So again, some amazing things about relativity that come out accurately in this movie. Inside Gargantua, there is a singularity. This is a diagram as seen by both beings. This is just my artist's conception of this singularity. It has a technical name, a BKL singularity. It's tremendously destructive. If you hit that singularity, you're dead. Your body gets torn apart in every which direction. You get stretched and squeezed in an oscillating way, first in one direction, then another, in a manner that's described by what is called a chaotic map in the theory in chaos theory. So really not someplace you want to go. But that singularity is governed by laws of quantum gravity. And so this carries us into the modern era, the subsequent consequences of Einstein's relativity. That there is something here we would like to understand. We can understand what happens as you get close to the singularity. The final singularity we do not understand at all. It's governed by these new laws of quantum gravity that are obtained by combining general relativity with quantum physics. And this is likely some variant of what we call string theory. And understanding these laws has been the holy grail of theoretical physics since about 1960. So a great challenge for theoretical physics. And these laws control singularities inside black holes, the birth of our universe, whether or not time machines can be built to travel backward in time. These are very important laws, which we really would like to understand. Now, in the movie Interstellar, maybe let me back up. I guess I don't have it here. In the movie Interstellar, understanding those laws is a huge thing because Professor Brand needs to understand these laws in order to be able to figure out how to control gravity in order to save the human race. So frequently in the movie you hear the actors talk about the quantum data inside a black hole that they want. These are really the laws of quantum gravity that can be learned about by going down inside a black hole and making observations. And so this is what happens in the movie, is TARS, the robot TARS, observes the singularity and its properties, deduces enough about the laws of quantum gravity to be able to send that information back to Cooper's daughter so she can figure out from those laws how to control gravity and use it to save the human race. So again, this movie involves deep physics that if you're a physicist, you can see it there, but if you're not a physicist, you may not notice it. There, in fact, are 3 singularities inside the black hole, and Cooper encounters just one of them, what is sometimes called the outflying singularity or the shock singularity. And I'm not going to go into these details, but only to say that we've only understood in the recent years that there are actually 3 singularities in here produced by stuff that falls into the black hole, generating these singularities inside the black hole. Okay, I already commented on that. So in my conversations with Christopher Nolan, he wanted to bring Cooper back to Earth from the black hole Gargantua faster than the speed of light. And when I told him that's not possible according to the laws of physics, he said, go home and do a real calculation. So I did. And I came back and said, no, here are reasons why you can't do it. He argued with me. He said, go back home and think some more. And after 2 weeks of this, he said, okay, I give up. I think I understand. He comments on this in the preface that he wrote to my book, my book about the science of Interstellar. It was a very interesting interaction. So I suggested to him, instead, you can bring Cooper back through the bulk. And so let's talk about the bulk for a moment. String theory, if it's something like that is correct, requires that there are 6 or 7 higher spatial dimensions than just the 3 that are familiar to us. And one of them could be a large dimension, but something big enough to maybe even have some science fiction adventure in. So to understand why this is called the 5th dimension in Interstellar, here I show then our universe as a 2-dimensional surface as I've shown it before, with one of the dimensions removed. In our universe, we have east, west, north, south, and up, down as 3 dimensions. Time is a 4th dimension. And the dimension reaching out of our universe, I call out, back, and that's the 5th dimension. And so in Interstellar, Cooper, when he falls into this, close to this outflying singularity, or shock singularity, he's caught by a vehicle called a tesseract, or hypercube, which has been placed there by the bulk beings who in the movie really do exist and inhabit this 5th dimension. I should say in the movie, these beings are called they. They, over and over again. They being said in a reverential way as though the actors were talking about God. They, once, near the end of the movie, the phrase bulk beings is used. And this says, it tells you something about Christopher Nolan. In his movies, and this is true of all of his movies, there are hints about what's going on, subtle hints that are there. If you watch the movie 5 times, you may catch the hint and maybe understand what's happening. And in this case, well, they are described as the bulk beings. So Cooper then is lifted out of our universe and carried back to Earth in the surface of a tesseract, where he docks alongside his daughter's bedroom. He is out in this higher dimension. Our universe is this flat dimension, 1 dimension removed, and he's looking at his daughter. He can actually see his daughter looking in that way, looking up across the top, looking down across the bottom at her. So he sees many images of her from light rays that go through the other faces of this tesseract. There turn out to be 6 other faces. So this is a still image from the movie. Cooper is here. One image of her bedroom is there. Another one is up above. Another one is down below. And it's just a very complex and compelling set of images of Cooper in the tesseract trying to communicate with his daughter. And I give you just this much explanation. You can read the rest of the explanation in my book. Let me say a few words about wormholes. Wormholes, black holes are real. We see them, basically. We see lots of them in our universe. Wormholes are speculation. They are named after the wormholes in an apple. If you're an ant on the surface of an apple, you can go from this side to that side, either across the surface, which is like staying in our universe, or you can go through the wormhole, which goes through a higher dimension to the other side. It's a shorter trip through a higher dimension. So in the case of our universe, here is a 2-dimensional slice through our universe. A wormhole reaches up from here to there. You travel along the surface of this wormhole. Since I've removed 1 dimension, you travel on a 2-dimensional surface. And you can go through the long way through our universe or the short route through the wormhole. Wormholes were discovered in the mathematics of Einstein's equations by Ludwig Flamm in 1916, rediscovered by Einstein and a colleague in 1935. But in 1962, Bob Fuller and John Wheeler showed that any wormhole will pinch off, it will collapse so fast that you can't get through it unless you put into it something to hold its walls open. That has to be something that repels gravitationally. It has to be some form of negative energy. The laws of physics do allow such negative energy, but they probably prevent you from placing enough inside the wormhole to hold it open. So wormholes, my guess is, are forbidden by the laws of physics, but we don't know for sure. People have struggled for several decades to try to prove this and have not got it all figured out. In Interstellar, this is the actual shape of the wormhole. And so we did a simulation with an IMAX camera looking through the wormhole, also looking around the wormhole, in order to produce the images of the wormhole that you see in Interstellar. You look inside this sphere, which is the mouth of the wormhole, you see the nebulae and stars and gas clouds in the distant galaxy very far away. Here is the wormhole near you with Saturn much farther away. So the wormhole is just 2 kilometers across. Saturn is very, very big by comparison, but this wormhole is close to you, so it looks big. I'm going to show you a trip through this wormhole. This is, again, from the simulations by the team at Double Negative, based on the equations I gave them. So you're heading down toward the wormhole. These are the stars and nebulae on the other side. This is one image of Saturn. That's the other image of Saturn. You're about to enter the wormhole. You're inside. You're outside. You're in the other galaxy. Now, wasn't that exciting? So when Christopher Nolan was editing the film, it was all shot. He had done all the filming. It was finished. And one day he telephoned me. It was in the spring last year. And he said, "Kip, we have a problem. Come to my house and let me show you the film clip from the team at Double Negative of the trip through the wormhole." He showed me a film clip like this one, not precisely this one. He said, "I have had the team change the shape of the wormhole and make film clips of the trip for all possible shapes of the wormhole. None of them are suitable for a great movie." He said, "What do I do?" And I said, "I don't know. I'm afraid you use artistic licenses," they say. You're going to have, for the first time in any major way, you're going to depart from what the calculations say. And so he did. And there is a trip through the wormhole that you see in the movie. Oh, gee, we have sound back, I think. So this is all the real thing. You're outside the wormhole, traveling around the wormhole. When he starts into the wormhole, it's changed to make a more exciting trip. So this is all real. This is all from the simulations. Skimming along the outside of the wormhole.
Everybody ready to say goodbye to our solar system? To our galaxy. Here we go.
Now it's changed. It's much more exciting. But it is remarkable that in this film, it's true to general relativity, very close to general relativity, except in this one major case of the trip through the wormhole. I'm going to finish by saying a few words about gravitational waves. These are ripples in the shape of space and time that are produced, for example, when black holes collide. Einstein predicted them in 1916. They travel at the same speed as light, according to his relativity equations. And what they do physically is they stretch and squeeze objects just like tidal forces do, just like gargantua's tidal forces do to the Miller's planet. The stretching and squeezing is perpendicular to the direction of motion of the waves. So if the waves are going into the screen, they stretch along this direction, squeeze along that direction. Then a moment later, it squeezes up, down, and stretches horizontally, then back to the original, and it oscillates. In 1958, Joseph Weber at the University of Maryland pioneered the attempt to detect gravitational waves. 71, Ray Weiss at MIT invented the technique that we are now using called the gravitational wave interferometer. And also in 1971, I and a number of other theorists began trying to understand sources of gravitational waves. And so we really date the things I'm going to tell you to 1971. And that's a long time. for a project that is now reaching completion. In the early 1980s, when we started planning this project, I had an artist draw a picture just from a sketch I did of two black holes orbiting around each other, colliding and merging. Today we have simulations of that. And I and others could compute that the power output in gravitational waves in that collision was enormous. It's 10,000 times more power or more luminosity than all of the stars in the universe put together in light. But this comes in gravitational waves. So when a black hole, two black holes that are small collide, that power output lasts for a very short time. The total energy that comes off is a few % of the mass of the black holes. If the black holes are huge, like Gargantua, or like the black holes in black hole in M87, then the collision may last for hours or even days. And a lot of energy comes out, but again, the total energy that comes out is a few % of the mass of the black holes. The power output is 10,000 universe luminosities. Nothing except the Big Bang that has that kind of power output in the history of the universe. It's two black holes colliding. And there are no electromagnetic waves, no light, no radio waves at all, except if there is a disk of hot gas around the black holes. The disk will be disturbed by the gravitational waves. And this offers an opportunity for optical astronomers and radio astronomers and X-ray astronomers to search for some radiation that coincides with the waves from colliding black holes. Details of the collision are encoded in the shapes of the gravitational waves. The stretching is up, squeezing is down. This black is a waveform that shows as time passes how much stretching and then stretching, then squeezing there is. This is from a simulation of these two black holes, one big one, one little one, 60 times the mass of the sun for this one, 10 times the mass of the sun for that. This is spinning at 91% of the maximum spin a black hole can have, this at 30%. They're going around each other. Spin axes are pointed like that, and they produce this waveform. There are two waveforms. Just as for light, there are two polarizations. There are two waveforms, both of which we want to measure, and then from the observed waveforms, comparing with numerical simulations on computers, deduce what was happening with the black holes, infer the properties of the black holes. The interferometer that Ray Weiss invented with some modifications due to Ronald Drever works like this. The gravitational wave pushes these mirrors apart, pushes those together because of a stretch in this direction, a squeeze in that direction. And then at the next half cycle, it pushes these together, squeezes those apart. In our instruments, the separation between these mirrors is 4 kilometers, and the motion of the mirrors is 1/1000th the diameter of a proton or an atomic nucleus. And this is unbelievable that these superb experimenters are able to measure that, and they can, and they do that today, make measurements over a distance of 4 kilometers, 1/1000th the size of a proton, as these mirrors move back and forth relative to each other using a technique called optical interferometry. So we have the Laser Interferometer Gravitational Wave Observatory, or LIGO. It's a collaboration of 900 scientists at 75 institutions in 15 nations, including 3 people, as far as I'm aware, 3 people at the National Tsinghua University here in Taipei. It's directed by David Wrightsey at Caltech. The spokesperson for the collaboration is Gabriela Gonzalez at the University of Florida. And this is a picture of one of the gravity wave detectors or interferometers. It's seen from an airplane in Hanford, Washington in the USA. There is actually a network of such interferometers. We have 2 currently operating in the US, in Livingston, Louisiana, Hanford, Washington. a test interferometer with much poorer sensitivity, which was used to develop the technology in Germany. In about 2 years, an interferometer in Pisa, Italy, called Virgo, will come online. And shortly after that, one in Japan called Kagra, and maybe a bit later, one of our LIGO interferometer, just identical to these in India. And so, but at the moment, there are 2 big interferometers operating. We require this network to be confident that what we see is real, to extract these waveforms, determine the direction to the source by what we call triangulation. We have built 2 successive generations of these interferometers. The first ones were simple interferometers, basically designed to be sure we knew what we were doing and perfect the technology. They operated between 2005 and 2010. Advanced interferometers, the things that are the real final instrument, were installed between 2010 and 2015. And they began their first gravitational wave search 1 month ago. These advanced interferometers have sensitivity good enough to see colliding black holes out to 1 billion light years from Earth. That's 10% of the way to the edge of the observable universe. That's what these detectors are doing today. It's really incredible. Over the next 4 years, they will be improved until we can see to 4 billion light years, a third of the way to the edge of the observable universe. It's really quite incredible. And we are likely to see lots of colliding black holes and neutron stars, engines of what are called gamma ray bursts, and there will almost certainly be some big surprises, things we did not expect. So this is a very exciting time. The first detection could be this year, or it might wait till 2019. It depends on how kind the universe is to us. But we are really quite confident that sometime in this period of the next 4 years, we will see the waves. And they will bring a revolution in our understanding of the universe. So for me, this is a truly exciting time in this area of studying general relativity. So I've given you some sense of what we have learned about warped space and warped time in these last 100 years since Einstein gave us his general theory of relativity. And I can only summarize what we have learned in this way. It is truly amazing. Thank you.